So let's get down to business. Translation. And like I said before, transcription, translation, they sound a lot alike, and it's easy to goof them up. But they're really quite different things. And so we want to keep them straight. The way like I said, I remember transcription is easy. You're just copying over. Translation is actually a more challenging thing, like translating from English to French or something. So today I want to talk about how that works. As a reminder, that's making protein based on the mRNA sequence. So to be clear, oftentimes we'll say we're making protein from RNA, or turning RNA into protein, and that's not what we're doing. We are reading the RNA and using that information to generate a protein. It's not a chemical conversion, it's a reading operation. So in the same way we talked about it before, the mRNA and the protein, you made a little table. mRNA has 4 letters. How many letters in the protein alphabet? How many amino acids do we worry about? A lot, right. It turns out there's 20. I'm really sorry about the noise. There's nothing I can do about this, because if I take this off, you can't hear me. So I'm sorry about the huge explosion sounds. Hopefully they will go away. There are 20 letters in the protein alphabet. They are, in mRNA, it's A, G, C, and U, and here it's ALA, VAL, LYS, etc. 20 different ones, it turns out. They're 1 strand in RNA and 1 strand in protein. That makes things a little simpler. This goes from 5' to 3', and this goes from amino to carboxyl. Right. A couple things. This is done by a thing called a ribosome. Okay. And that is a complex of protein and what's called rRNA, ribosomal RNA. So if you were going to be consistent in how you named it, you'd call it protein polymerase. Right? The thing is, it turns out, historically speaking, they discovered ribosomes long before they knew what they did, because they're actually quite large as cellular organelles go. So there were these things called ribosomes. Ribo, because it contained a lot of RNA, ribonucleic acid. We now call it the rRNA, the ribosomal RNA. Later on, they figured out that those things are actually where proteins are made. So they have a sort of archaic name. The other thing is, because there's a different number of letters, the translation can't be as simple as transcription. Transcription, it was just every time you see an A, you're going to pair a T, etc. Right? That's easy. 1 for 1 letter. In this case, you've got a 4-letter alphabet you're trying to turn into a 20-letter alphabet. So you can't read 1 for 1. So therefore, you need to read the mRNA in groups of nucleotides. These are called codons. Okay? And you can actually do a little bit of math. And this is one of the kind of cool things. The number of nucleotides per group, that is per codon. Okay? And the number of amino acids that can be specified. Right. And this must be at least 20 for all 20 amino acids. Right? So if you have 1 nucleotide per codon, you can specify 4 different amino acids. You could have an amino acid for A, 1 for G, 1 for C, and 1 for T. That's only 4 amino acids. That's nowhere near the 20 that you need. So what about if you had 2 nucleotides per group? Well, then you could have a G, a C, and a U, GG, GC, GG, and GU, etc. If you work out the math on that, it's 4 times 4, is 16 possible amino acids. Both of these are too few. They're not enough for the 20 amino acids you need. If you, on the other hand, you do 3, it's 4 times 4 times 4 is 64, which is more than enough. And this is one of those cool things. Lots of times biology is just so. It's the way it is. You have to live with it. It doesn't always make sense, but that's the way it is. This is one of those few things where it actually makes sense. That is the smallest number, the smallest possible size for a codon that can encode all the different 20 amino acids is 3 nucleotides. And it could have been that it were there 27 long, but there's lots of extra, right? But it turns out, in this one particular case, 3 is exactly right. That is, 3 is just what you need, or it's a little more. It gives you more than enough capacity, but that's the way it is actually in real life. Therefore, there are 3 mRNA nucleotides per codon. And again, it didn't have to be sort of as neat as that. And when the Watson and Crick and all their buddies were working on this, they thought, wouldn't it be cool if it was 3? The math would work out kind of nicely. And it turns out that it does. It didn't have to, but it turns out that it does. So the other thing you need